Good day, everyone. I'm Francis Royam Genelsa back with another interesting scientific innovation. My report will be on spider silk modification and will focus on Lepore and Friends' unique study, spider silk reinforced by graphene or carbon nanotubes from the University of Trento. Spider silk is a multi-million-dollar business. The thin strand that gets tangled in your hair on brisk morning walks finds excellent use in a lot of industries. The most frequent example is its use in bulletproof armor, rivaling the projectile stopping abilities of Kevlar, a synthetic polymer. Spider silk's popularity is due to the intersection of a few key factors: high tensile strength, excellent flexibility, and biodegradability. However, spider silk is tricky. For one, although the biopolymer is strong, it pales in comparison to some synthetic polymers which exhibit better tensile strength. Scientists, therefore, have been trying to find ways to reinforce silk to improve on existing properties, such as mechanical strength, or add entirely new ones, like electrical properties. However, most of these trials have only led to failure or, at the very least, lackluster results. This is because of spider silk's second problem. It's notoriously impossible to replicate, at least so far. Spider silk is mainly composed of proteins, and treatment of artificially synthesized silk has been difficult because of its viscosity, which makes it difficult to draw into fibers. The first scientist to patent an accurate and reliable way of reproducing spider silk would be a millionaire. Lepore found a way around this problem with a very unique methodology, which can be summed up as make the spiders do everything. In their study, they placed spiders in water loaded with graphene and carbon nanotube dispersions, effectively feeding them extra strong derivatives of carbon. Then, through some extremely complex spider stuff, these materials in their diet get incorporated in their spider silk, producing naturally reinforced threads. In essence, the team was able to gloss over the manufacturing problem of spider silk and its subsequent treatment in a pseudo-artificial manner by letting the real experts handle it. Now, did they actually get good products out of the entire ordeal? Well, yeah. These graphs are the results of their mechanical strength testing and show how the reinforced spider silk variants are better than the reference spider silk. The group used 3 different additives and compared the effects each of them, when bonded with the spider silk, introduces. In general, they were able to create silk strands that were superior to natural spider silk. The graph on the left shows how the stress-strain curve of the modified spider silk variants show better tensile strength and toughness modulus values. These improvements are quantified in the set of 3 graphs down here, which show the increment in percentage of the variance over the reference silk. You'll notice that samples spiked with carbon nanotubes produce a greater change in the properties of the silk. Finally, the graph on top is a comparison between varying synthetic and natural fibers, including the spider silk produced by Lepore et al. It also includes limpet teeth, which is currently the strongest biological material found in nature. Limpets, which are snails, use these tiny teeth to scrape food off rock, and while the material was hailed as stronger than spider silk, it sacrificed toughness for this incredible strength. As a result, limpet teeth are extremely brittle and fracture almost immediately when you go past their yield strength. But now, the spiders are back and better with their new and improved carbon-enhanced silk, which has a tensile strength comparable to that of limpet teeth, but with better toughness. These things won't break easily. Now, the patents I've found aren't all that spectacular. As mentioned earlier, spider silk is difficult to work with, so here's a patent by Kaplan et al., which details the artificial modification of spider silk. They worked around the common problems found when playing with spider silk by introducing an autoclave method of electrospinning, which doesn't use organic solvents, which are not biocompatible, and minimizes conformational transitions in spider silk, which happen during certain procedures. But enough of that, let's look to the future. What can we do with super strong spider silk? A lot, actually. It can be used to create bulletproof clothes or strong rope materials. Sports could also benefit from strong and flexible materials. Baseball gloves made from spider silk? Solid. But my personal favorite is its use in biomedicine. Spider silk can be used as a hearing aid because it's extremely sensitive to airflow. If you coat it with metal and stick it in a magnetic field, you could sense sounds as low as 3 Hz. Spider silk can also be used as a bandage and for artificial tendons. Spider silk, at the end of the day, is a very flexible material.